Hello, everyone. Welcome to the second talk of today, Popular Science Talk. We are pleased to have Dr. Rakhi Singh to deliver the talk. She is a faculty in the Department of Mathematics at IIT Madras. She is currently working on supersaturated designs and subdata selection for high dimensional data. Today, she is going to talk about sifting the sea, finding just enough to predict from too much. Let's welcome her for today's talk. Thank you.
All right. Okay, so you all sort of have seen me for last 4 days. So yes, I've recently joined IIT Madras, and I'm a statistician, which Dootika is another statistician. Siva is probabilist, probably here less or equal proportion of mathematics versus statistics. So before I get started, how many of you had any course in statistics, or which course before coming here? St. Xavier's. Okay. Anyone else? And other people have not had any course in statistics, right? Not yet. Regression you have heard? A little bit? Okay, good. So that's all we need. How many of you are interested in AI ML at the intersection? Okay, not too many. But so I would urge you to, even if you are interested in pure math, I would urge you to try to pay a little bit of attention to my talk. And I've tried to keep it simple and not use jargon. So many times we see people, I'm sure Dootika gets those students too, who have done PhD even in pure math, but they want to do a smallish project in AI, ML, statistics, data science, something so that they have a better position in the job market for them. So AI, ML starts from, well, loosely speaking, it starts from doing a regression. It starts from trying to predict some behavior in the data that you see. Okay, so that's what we'll try to talk about today. And we have had a great, by the end of it, I'll tell you an algorithm, and then you can decide if my algorithm is parallelizable or not, or maybe embarrassingly parallel. I hope not, no. So we'll see. Okay, so the topic that I want to talk about is sifting the sea, finding just enough to predict from too much. It's a very popular title, but a more technical title would be sifting through big data and how to select just enough for effective prediction. So that tells you that I'm interested in some sort of prediction problem. So what do we understand? Can anyone tell me what you understand from prediction, maybe? For some example you can take. Anything that you want to predict in your lives? Something that is predicting the population, okay, by analyzing some data. Yeah, sure. Predicting how much marks you will get in the Sunday test? No? Yes. Okay. So all of this is, of course, examples. Prediction has some key features, and we'll talk about them in just a minute. So we want to do a prediction. We want to do it effectively. What this means is we want to be as close to what reality would be, because prediction, as the name suggests, we are trying to guess or make an estimate of what the reality could be. So we want to make it effective in the sense we want our predicted value to be close to what the true value might be. So that's the underlying task that I'm trying to do, prediction effectively. Now, people, statistics, computer scientists, data science, ML, all of us have been doing prediction for a long time, more than 100 years. So what is so different today? So we have access to very large data sets, right? So we'll give some example, and then you can realize how large the data sets can be. But we don't want to use all of the big data that we have. somehow we want to sample this big data and work with a smaller set of data. So Maithili mentioned how parallel computation can reduce computation time, but I don't want to do, I mean, maybe I want to do parallel computation as well, but I want to take a sample of my big data and just work with this sample to see how I can still make an effective prediction rather than using a very high powerful machine, right? Because all of us don't have access to a powerful machine, but we still have to do computation, we still have to do prediction. So how can we sample big data so that we can still do computations in a reasonable time with whatever machines we have access to? And of course, this problem becomes compounded, and even on high performance computing, you want to make it a smaller big data and so on. Okay, so let's get started. So I'll give a brief introduction, and then I'll talk a few methods that exist for model building, then some prediction I'll talk about, and finally I'll introduce our method a little bit. Okay, so let's start with the terminology here. So prediction and classification are two problems that arise in everyday life. So for example, Gmail or any email server that you use, it predicts whether a particular email that you receive, it's a spam or not, right? Or your phone tells you whether this message is a junk message or not. So that's a spam classification. In simplest terms, you can use some model, which is called logistic regression model, to predict whether this particular mail will be spam or not. This has become very old problem, by the way, spam classification. So it's very matured problem. But something that might interest you more if you watch movies is the movie recommendation system like Netflix. Whenever you are watching a movie, it will tell you what next to watch. Or Amazon, right? When you're buying a product, it will tell you what next to watch. So how does it tell you what next to buy? Amazon, for example. And it's doing some model and everything, sure, some data science ML, but what are the raw ingredients that it's maybe using to predict that information? One person. Your history. So what have you ordered? But how will it use that? Because if I have ordered shoes, then I am less likely to order shoes in the next time. Same products, huh? So in the more Instamart kind of things, you can say on a monthly basis, you will need the same product. So, okay, your own history is one. What else? What other people who bought these shoes, same thing, what else they bought? Maybe they bought socks, maybe they bought hiking gear, whatever, right? So your history, other people's matching patterns. So all of these are called independent variables or features that are helping you predict the goal, right? So in the movie recommendation system, so and some more examples, let's talk. So predicting when traffic will clear on Google Maps, right? So that you can decide what time you have to go somewhere. Okay, and so prediction and classification are in the similar framework, so to speak, but when related, so title, genre, release year, who are the actors, actresses, popularity, some user-related features, which are age group, what do you prefer, how much time you watch, which time you watch, typically, and then some interaction-related features, which means how did you interact, how did this particular user interact with this particular movie, right? I might like rom-com, so I might watch it entirely, but I might not like action movies, so I'll start maybe exploring and just switch it off after 10 minutes. So my interaction with movies is different based on what I'm trying to do. Okay, so this is how typically our data would look like. So we are interested in what is called structured data, which means we have this nice tabular form data. So we have some rows, some columns. It looks like matrix, but it's not a matrix when you store it in R. Can anyone tell me why not? Anyone has done any coding other than before coming here? Then maybe you have heard the data structure. So why is this data, why can't we store this, even though it's looking like a matrix, can I store it in R in a matrix form? Different data types, right? It's a data frame because these things may be some numbers, some characters, so it's a mix of it. So it's not just a matrix. You can't do A plus B or matrix operations, right? Okay, so throughout the talk, I'll denote the number of rows or observations that I have. I'll call rows as observations by n. So in previous case, I have these user movie ID, those are my rows, and columns by p. Okay, so I have two kinds of data. So the typical data sets could be two kinds: tall data, which has a lot many rows, but the number of features are small. Or it could be wide data, where you have a lot of features, but number of observations is small. So an example of this could be biological data. You are trying to study whether someone, what is the likelihood of someone having a particular disease or not. So you have only a few patients, but you have a lot of variables related to the gene sequencing and stuff. So what we are interested in for this talk is essentially the data which has both large N and large P, but still our N is of the order of billions, or at least millions, but P is just over 1,000. So P is large, but not that large, but N is really, really large. So you can imagine that, for example, Amazon or Netflix, the example that I gave, collect a lot of data, right? They have a lot of users, there are a lot of movies, so they'll have millions and millions of rows. So what is the problem? So we want to predict next movie, sure. We can use all data to predict, and maybe we should be using all data, entire data to predict the next movie for you, because that will give you ideally the optimal result. But why don't we do that? So one problem is, of course, of the computation time. So so N is too large in the sense of it will take a lot of computation time, it will take a lot of memory usage, and you want to optimize on all these things, right? So ideally, also what I want to do is this data reduction, where I'm saying that for large N, I'll select only a small portion, which I'm denoting by K, and I'm calling this a sub data of my big data, of the full data for further analysis. So I have these this n by p data. For the purposes of this talk, we'll just reduce the rows. So we'll select a few rows somehow, and we'll work with this data of size k by p. And we are assuming that our k is much, much smaller, so that we can run ML method or statistical learning method in reasonable computation time. Actually, I can give you some numbers here. So I think I had a data set with only less than 5 million observations and reasonable variables, like 100 or something. And running a random forest on this, on a still decently high-end machine, took almost 24 hours, which we cannot afford, right? If we are trying to run, we want to do it fast. So we'll work, so that's the basic theme of why we want this subdata. So we are not deciding for this talk how large should this K be, how many rows should we select, we are not deciding that. We'll fix a K that our computers can handle, let's say 1,000. But now we want to decide in this talk which K points should we select, which 1,000 points out of a billion points should we select, so that our prediction result is close to what we would have gotten for the full data. Okay, that's simply the problem. Okay, so what is the first method that comes to your mind? So I have, let's say 100,000. Let's work with some numbers here. So my small capital N is 100,000. So I have these many observations, and for the purposes, we don't really need number on P, but let's say P is 100. And now I want to select, let's say 1,000 rows out of this matrix of size N by P, 100,000 times 100. And I want to select 1,000 by 100 matrix out of it. So what is the first thought that comes to my mind? Your mind. But for a general data set, because we are not restricting to the problem. That is very advanced. What is the first thought that comes to your mind? We learned the sample function, no? So what does sample function does? Just random selection. So very first thing that we can do is just randomly select, do sample. So in this, I've made numbers even smaller. So I have 100 points and I want to select 8 points. So I just say sample 1 to 100, 8 points, and I do replace is equal to true, so that you can argue that I should probably do replace is equal to false, but I wanted to select each point with equal probability of selection. So I have kept it 1 by n, but for really large data sets, it doesn't matter whether you do replace is equal to true or false. But just to get some theoretical results, people typically do replace is equal to true. Okay, so this is the simplest thing you can do. Of course, there would be some repeated points, doesn't matter. So our data set is not exactly of size 8. But because small k would also be pretty large, it doesn't matter if we are not sampling exactly k points. Okay, so this is very easy to do. No worry about time computation, very fast. No worry about memory. You don't even need to load the entire data set into your memory. No worries about computational complexity, anything. Very simple, very fast. What is the problem? Why do you want to do clustering? Why not just do random selection? It won't be specific to the person, sure. So in general, it will end up not giving great results, right? We are trying to predict something. It will be so if we just look at these examples, I want to predict, take some point, maybe it will select some points here, but they might be very off than what I'm trying to predict. So I'll not get a good result, which is obvious, right? You're not making any effort. Why should you get good result, right? Okay, so we can do something slightly smarter. So this title was that model building, right? So I'm interested in building a model. So what kind of model I'm interested? So in the beginning, let's say I'm only interested in building a linear regression model. We'll do more complicated things, non-parametric, clustering, all of this we'll do later. But for now, let's say I know that the relationship between my x and y is linear loosely. And so these are my data points. So x is, I don't know, you can take any example. Number of hours you are studying in the summer school after going back, and y you can take is the marks you will get in the test, right, on Sunday. Okay, so what do you hope? The more number of hours you spend on this test, will you get more marks or less marks? More marks, right? So you hope the positive increasing linear relationship, right? Can it be like this? That the more number of hours you study, or maybe this still can be, but can it be this? It can be, but hopefully it's not that the more you study, you go down, right? So hopefully it goes up. So in general, so we are working so far with the very simple model that the more hours you spend, more marks you get or more progress you make. So this is a regression that we want to do. Okay. So this is the simplest case where you only have x, one variable, one independent variable to predict your marks. But in general, you can have many more variables to predict the marks on quiz, right? How well you did in homeworks, how well you did in class, how much you interacted. All of those can be features. So in general, regression model is written something like this, and will not necessarily talk in a lot of details. But one thing you should keep in mind whenever we are using linear models is this is a simplistic choice, right? Because when you are doing linear model, what you can sort of the kind of behavior that you can predict is just loosely again, just sort of this linear relationship between x and y, right? If you have to predict something else, something quadratic, then you have to make a lot more effort, but you might not know what is the true relationship. So when you are assuming that you are fitting a linear model, that means you are making a simplistic choice. But for now, we'll believe that that simplistic choice works and see how to do subdata selection, how to select a small number of points from this data. Okay, so we'll look at the first graph on the both sides is the same or similar at least. Okay, so I'm gonna, so let's say these are how so many points and I want to select 4 points. Okay, and I have 4 points on which will be my new points or really the old sample of the old points, and I want to build a model based on only those points. So what if I select, so what is the line first of all in this? So maybe we'll draw something like this, right? This is not linear, my line, but something like this would be drawn, right? Which will be the optimal line. So what if I select, let's say I select these 2 points and these 2 points. So I want to select 4 points in my subdata. What are the different, so now your new graph only has these 4 points, right? So you ignore the other points because your subdata has these 4 points. What sort of lines can you fit here? What is the best line here? So I'll fit this, maybe this. This won't go through all 4 points. So we are trying to fit a line which can approximate these 4 points well, right? The relationship between these. So it has to go somewhere in the center. It can also be like this, which will be close to what we have. But I think all these lines will sort of be equivalent here, right? And so if I make this line, then will this be close to my true line? No, right? I can do a very terrible job. So this is not smart. I might as well have picked 4 points randomly. That will do a better job than this smart, so-called smart selection. So which 4 points should we choose so that we can approximate this line well? Which 4 points will you choose? On the line, okay. So on the line is one answer. Let's see which points you should choose. Okay, so on the line is these 4 points. And someone said extremities, right? Okay, so on the line and extremities. Which of these are better? So on the line, in this case, it's looking to be better, but actually on the line could be making it worse because maybe I chose these 4 points, which are also almost on the line, but the extremes could become very weird on the line. So actually the theory tells us that if you select extreme points, then you are able to fit a very close approximation to what you would from all the data. So that's one of the, or rather 2 of the smarter methods. I'm not sure if this is 26 minutes left or happened, but anyway, it doesn't matter. It's 50 minutes. Okay. Okay, so so there is one, for people who have done regression, there is something called as hat matrix or the leverage values, which tells you how important each observation is for predicting its value. So this is the similar concept to this guy where we are choosing extreme values. So ultimately, one method which is called leverage sampling chooses the points based on the higher value of this guy. So again, we are doing the sampling function, but we are giving it the weights which are based on these leverage values. So this is great. This is also a good, this is a good method, first good method. It's better than uniform for estimating model parameters. There is some problem here. Can you, so for being able to compute leverage sampling, you will have to compute this matrix and compute its diagonal values. So any problem that we see, after the previous talk, we heard that matrix multiplication is all AI and ML are doing. So so this should be done fast, right? But I'm saying that computational cost, well, I'm also giving a hint here. So matrix inverse is still a very difficult task for a computer, because for matrix inverse, you know SVD, so you can apply SVD and make your life a little bit simpler. But even computing eigenvectors and eigenvalues is not, because these are really big data sets, right? So matrix inverse is a very open ended research problem, how to do it fast. Whenever there is a matrix inverse involved, even though in this case is P by P matrix only, which is not super large, but matrix inverse can become really complicated and can take really a long amount of time. So that's one drawback of this method. So what people did next, using what I also do, which is the field of statistics, which is called design of experiments. So they did something, and we'll not talk about this, but we'll talk about, they call their method IBOS. And what they do is, for each variable, you select extreme values. So in this case, we saw that extreme values selection is ideal, right? But I only have X with Y, and I'm only selecting extreme values for X. What if I have X1 and X2 and X3? How will you go about selecting extreme values? Because you have to select extreme values for X1, then go to select extreme values of X2, then go to select extreme values of X3, and so on. So that's what this method is doing. But the problem with this is this loses the correlation. So if X1 and X2 are correlated, there is some relationship, then you lose that information because you are treating each variable independently. Right, so what this method is doing, so suppose I have P is equal to 4, so I have 4 features that and I want to select 8 observations, so my K is 8. So I compute this number, K over 2P, which is 8 over 2 times 4, so 1, and I select one smallest and one largest value per feature or per independent variable. So I sort my X1, I select this smallest value, so I select row number 93, I select row number 80, I delete this from my data set, do this again, so go to X2, sort the data based on X2, and select this row for its smallest value, this row for its largest value, and so on. So it's great method, it works theoretically, it works simulation-wise. The only challenge is when our variables are correlated with each other, it's a little dicey because you might be selecting sort of these cluster of points. So if the variables have a positive correlation, then you might be selecting these extreme points a lot more. And this might not reflect the true behavior of response. So we are selecting extremes, that's no problem, but it might not reflect the true behavior. Okay. So I think I'll not show you these simulations and theory, but I want to show you some methods which, okay, so when we build a model, we can use that model to predict, right? I have built a model, I know the relationship between Y and X, you give me a new user, I'll be able to predict this movie preference for this new user, right? By using the existing model. So here I'm solving a prediction problem in a roundabout way, right? In all these methods, my focus is on building an accurate model. All my theory is in building accurate model, and then I'll use this accurate model to predict a new data point. But can we not do this directly? Why go this roundabout way? In this roundabout way, we have made a stronger assumption that we know that linear relationship is true, which may or may not be true, right? So that's why we want to focus a little bit directly on prediction. So maybe in the sense of doing ML models and seeing how we can build better subdata tools for ML methods. Okay, so K means clustering. How many of you have heard? What is K means? Just very roughly. It's okay, say wrong thing, it doesn't matter. Okay, good, at least you have heard the term. Okay, so here this is an example where I have some X, it doesn't matter what it is, some Y. So what happens is when X is minus 1.5 to minus 0.5, Y is flat. Suddenly there is a peak here, and then y is again flat, right? It's close to 0. So what k-means clustering does, so it's one-dimensional data set, right? K-means is just working on x. So what k-means will do, it will take this one-dimensional vector that you have, so real line, in this case minus 1.52 plus 1.5, it will just divide it into consecutive pieces. So in one case, it's just doing linear spacing, that you are using sequence command in our SEQ command. So it's just doing the same thing, linear spacing. So here we are selecting these 30 points, which are represented by these crosses. Okay, so what is k-mean doing? It selects one point, then go to the next point. It just divides this range into 30 equal buckets and choose one point from each bucket. So why do we see a point here? Why do we see a point here and not here? There's just a representation, no? It's actually on x-axis, this point is right here, right? But the data we are choosing to plot this point, like text that I have plotted, this plotting character is on y-axis, so that's why it's here. But in x-axis, I'm taking the point here. Okay. So can I use this k-means, the clustering algorithm to, so how good is this method if I were to use this for prediction? So I'll have these 30 points, right? These crosses in my data. I'll not have more points in this region. So how will I do if I'm predicting a new point for a new value I'm predicting in this range? How will I do? What do you think will be the prediction for y if I take a random point here in between these two crosses? What will be my prediction? 0, right? So pretty good, pretty close. Here also I'll predict something 0. So I'm predicting as a neighbor. So you think of k-means as a prediction in the neighborhood. So you pick a new point, let's say exactly at minus 0.4. You look at the points in a small neighborhood and take average of y in that neighborhood. So what will I do? So here I'll predict 0. Here I'll predict 0. What will I do somewhere here? What will I predict if I have a point exactly at this point? Huh? Around 4, 5, around this point, right? Okay, but in reality, my actual observation is 7 or 8. So it will be terrible, right? And depends on if I had multiple spikes, that would make it worse. So this is a very simplistic example that it does seem to do well for a lot of data points, but for the spikes or wherever there is a volatility in y, wherever variance of y is high, k-means wouldn't work. Right? This is again same type of example. So this is a contour plot. So x1 and x2 are our two independent variables. Both vary on the same range as last, right? And so these colors represent the volatility in y. So these pink areas are where there is not much volatility in y, just like these areas, right? So y is whatever, its variance is small. This blue area is where the variance in y is very high. This white area is where the variance in y is second high. So if I do k-means, what it will do is it will take this 2 by 2 grid and divide it into these so-called Voronoi partitions and pick a point from each of these partitions. So again, the same thing as before, that I'll do a terrible job at predicting this area where there is a lot of variability in y. So what should we do? Can we design a method so with this argument, what do you want? What kind of sample would you select? And by the way, here all dots represent the points in the sample. And this entire space is the full data, is the big data. So what sort of points would you want to select? So I'm saying, so here, so let's go even simpler. Here, what kind of points? So here, if I have to select, let's say 30 points. What if I select only 10 points here, but I select 20 points in this region? Then I'll do a much better job. No, I'll have a lot of points in the neighborhood. I'll be able to approximate the true relationship. So that's what is ideal, that wherever you have a higher variance in your y, you select more points, and wherever your response is sort of flat, you select a few points, and that's good enough. Right, so that's what these people Joseph and Mack proposed their method. R super compress is what they call it. So they select much more points in these high volatility area, and they select a lot less points in these pink areas. Great, right? So this is what we want. This is ideal scenario. This will lead to a good prediction model. Some of the cons which you may or may not be able to think at this point is this method works on using Euclidean distance. Typically in higher dimension, Euclidean distance does not do a good job. So you need to find a better distance metric. Another problem with this method is that it is computationally very slow. Even if you have 5 features, it can take 2 hours to compute, even on like 10,000 observations only. So this defies the whole purpose of doing subdata, right, if it is super slow. Okay, so to avoid, and then there are a few more methods. Okay, maybe I'll tell one more method before I tell our method briefly. But keep this in mind that we want this property that higher volatility areas, we want to select more points. Lower volatility in Y, we want to select less points. Another thing that you can do is, have you heard about distributions? Some statistical binomial distribution we talked a little bit about, right? So sometimes what people want to do is you have this big data, you see what distribution it follows, what joint distribution, and we want to mimic this same joint distribution in our sample, right? But first of all, we don't know in real data what is the distribution, right? So we are, it's a sort of a chicken and egg problem. So what one of the methods, which is actually very efficient, does is that so these are all the points in your big data. Okay, I think these are 50 points. Right? So these 50 points are points in your big data, and now you want to select 10 points. So what this method does is it starts from one random point. It makes a convex hull using something called as energy distance around that of size 5. Then it will go pick the next point which is closest to this, this hull and make the next hull. Okay, so doing like this, it will divide the space of 50 points into 10 hulls. And then from each of these convex hull, it will select 1 point, which was the starting point, but it could be also any arbitrary point within that convex hull. So the claim is that this method works in mimicking the joint distribution of the sample. And this works pretty good in p-dimensional space. It is able to mimic the distribution. Of course, if you think about it a little bit, uniform sample is also mimicking the joint distribution, right? Because if you are selecting the points randomly, if your uniform sample is large enough, you don't need to do this because that will already represent your population well. So what is the advantage of doing this? So if you have a small, if you want a data set with a smaller size, then this is better because then uniform can be a hit or miss, right? So this was great, but what we were able to show is that this is great if you want to mimic the distribution, but it does not work quite well for prediction because when you are predicting, so let's say, okay, this time I'll use this board. So if I'm predicting from this data set, so I'm interested in this data set where I just have X and Y, and maybe I have 2 points here, and I'm interested in model building or prediction, then you said that I'll select extreme points, right? That was an easy case. So extreme points, will you select now in X or in Y? So if I select, so this is clear, but if I select these points, then I'm gone, right? Then I can't be predicting this line. Then my line would be somewhere here, which would be very bad, right? So we have to still do a little bit of trickery to get the right points. But the major point is if you were to mimic distribution, you will actually select some points from here, and then you will select some points from this region, which means that your final model as a result would not be great because of these outliers, right? So mimicking the distribution doesn't always work for prediction problems. Okay, So finally, what do we want? What did we do? Okay, first, what do we want from our subdata selection method? Because this is a very new area, by the way, of research. I mean, it has come up in last 5-6 years only. There are multiple papers, but it's a very new area. So it's not established science yet. So, okay, so one thing we want is when responses are available, we should be oversampling in the higher response volatility areas and undersampling in the constant response areas. And of course, we want our method to be computationally efficient, because if it's not computationally efficient, there's no point in doing this. We also have some wish list, right? It's my wish list, so it can be as large as it is. It should work for a large number of variables, for a mixture of continuous and categorical variables, regression, classification problems, and should have no assumptions. It's too much to ask for. But luckily, we have been able to find a method which works for a lot of these cases, mostly because we use binary decision trees to create a partition. If we use binary decision trees and then we use random forest to do this, then we don't have to make model-based assumptions. Our method inherently works for categorical and continuous variables. By the way, all the previous methods that I discussed only work for continuous variables, so no method for categorical variables so far. And its binary decision trees are super optimized by now. So our method by default is computationally fast. And so I think, let me see, I have a couple of minutes. Okay, so do we know decision trees? Someone? No? Okay, so I'll give a very brief 1-minute overview on decision trees. So decision trees are called decision trees because they make human-like decisions. So here we are trying to predict a baseball player's salary based on their years of experience and based on the hits that we do. Of course, this is US data and not Indian data, otherwise this will be cricket. But you can you can think of something, I don't know, batting average or something, and number of years of experience, right? So, and then we are trying to predict the salary that they'll get. So decision trees would decide that for years less than 4.5, the salary would be, let's say, I think this is 5.11 million or something per year. Maybe sounding a lot. I'm not super sure of what the units are. But okay, so they are making the decisions like years less than 4.5, you get some salary, but if your years are more than 4.5, then further, if you have the number of hits or hitting average, the number of hits that you made in previous year is less than 117.5, then the salary is of the order 6, but otherwise the salary is almost of the order of 7. So you can imagine that the higher the batting average and the higher the number of years of experience, you will get higher salary. The player will get higher salary, right? So decision tree have this. So these are called binary decision tree because on each step we are making either going left or right? So all our splits would be of two kinds. Either years is X, some variable is less than something or greater than equal to something. And we continue to make this tree. We can in fact use a very big tree as well. So decision trees, because they are making human-like decisions, right? It is something easy to understand. The linear model, sure, if you have mathematical aptitude, it's easy to understand, but otherwise it becomes a little bit tricky. But decision trees, everyone can understand. You can give it to anyone and they'll be able to run through your data set and be able to make a human-like decision. Okay. So one thing about decision tree is that they are able to create a partition of the space, of the partition of the feature space. So here, so let's see, so we have years and hits as example. So what is partition? Where the pattern, huh? So we learned two terms in probability worksheet, which said mutually exclusive and exhaustive, right? So that's what is a formal definition of partition, that you are able to divide it into parts which are mutually exclusive, so there is no common point, and it's exhaustive, as in it covers the entire space. So we had this previous example. This is also a partition, right? This is this space, all of these lines, this Voronoi partition is partitioning the data set. With decision tree, you will not be able to create such partition, but you can create these so-called axis-aligned partition. So around x-axis and y-axis, you will have these partition, right? So x is, years is less than 4.5 or more. So this is first region. And then within years more than 4.5, you will have this region of hits more than or less than. You can do it in any p-dimensional space. Any decision tree decision tree will give you a partition of the space, which is great, which is a great first step for our method. Okay, so it's a little bit difficult to explain this method. I was being a little bit too over-optimistic, I guess. But what we essentially do is we find the best partition of the space, and then based on a partition, we decide how many points we want to select from each of the cases, from each of the sector of the partition. And then we also tell how to select each point. So, but the moral of this story is that after we apply our algorithm for the same example as before, we select these black points. So how do these look? Similar to what we had before, right, with the other method, which is great, which is what we wanted. But the advantage of our method now is that it can work in higher dimension, and it can work it computationally very fast, and it works for categorical and continuous variables. So we have been able to achieve the same goal in a much broader space of problems. Okay, okay, so that's my last slide. So selecting a subdata is a newish problem and is an important research area that has emerged in last 5-6 years. So if any of you have any brilliant ideas, please work on this problem. Please write to me and we can work together. Or you can also take this back in whichever institute you have come from, and try to play and see which problems you can solve. And well, there are multiple open problems because this is a new, by virtue of it being a new area, but I consider the most important problem is to do this in a non-parametric space where you sort of don't make any linear model based assumptions. So there are, I would say at least there are 200 papers on this topic of subdata selection, and at least 190 of them would be using some model-based assumption. So the research in this model-free zone is new, and it's more important because really in big data, you never really have linear models. You can use linear model as a starting point, but it's hard to generalize from it. So people are often using decision trees, random forest, neural networks, and so on. So that space is wide open. So please work on it. Please choose statistics, do some project in statistics. Okay, so we'll stop here. And if there are any questions, I'm happy to take them.
Thank you, Professor Rakhi, for your talk. Please feel free to ask any questions if you have.
So maybe not the optimal most solution, but you at least want to come up with a few solutions. Because if Netflix starts showing you only one movie recommendation, which is your optimal movie recommendation, you may or may not choose it, and their whole recommendation system will crash, right? So always we assign certain probability. So we are saying that you will watch this movie with, say, 90% probability, but these movies you'll watch with 80% probabilities, and then we'll assign some probabilities to all the movies, and then based on that, we can show you selected set of movies. Because today I'm in mood of watching something which Netflix will not know, right? But tomorrow I might be in the mood of watching something else. So it's a big list of movies which are all the possibilities with certain probabilities, so that they'll do a random permutation and give a random, but within the class of near optimal movies.
Any other questions?
Question?
If there are no more questions, let us thank Professor Rakhi again.